So this problem is from stochastic processes, but we could treat this as a simple Fourier transform problem. So you're given few autocorrelations. In fact, we don't even know which ones are autocorrelations. So these are 4 sample problems. We want, if they are autocorrelations, then the power spectrum is given by the Fourier transform of the Wiener-Khinchin theorem, Fourier transform of the autocorrelations. So one way to find out whether these are autocorrelations or simply find the Fourier transform, which should be the power spectrum. And power spectrum, of course, should turn out to be non-negative definite if these are valid autocorrelation functions. So this is some of these problems are interesting. Notice that there's a Sinc here. So this is, of course, if you draw the picture, it's a damped sinusoids, this one. This also looks like that because Sinc also is damped, and the Sinc at the origin is 1. So this also looks, but completely different functions. This is not sine, this is cosine, oscillatory. And the damping alpha is positive, then it, of course, damps like this. So this is more classic. This is we know it's an autocorrelation, it's a damped sinusoid. So if you have, whereas this we have to see when it will be an autocorrelation function, etc. In fact, so let me start by, so Fourier transform is, of course, the Fourier transform of autocorrelation function, or Fourier transform of any function is this, r tau e raised to minus j omega tau d tau. So from here the inverse relation is r tau is 1 over 2 pi minus infinity to plus infinity s of omega e raised to j, classic expressions, d omega. So I just want to say that just to show, anyway, this may be useful to us. So let me replace this by u because it's a dummy variable, and bring in the duality property. And t is a variable on both the sides, so I'm going to replace it by omega. That's still valid. And now u is a dummy variable, so I'm going to replace it by tau. And I'm going to bring in this 2 pi here. So this is a classic result. And then if I replace omega by minus omega, notice that this looks like the Fourier transform of s of t. So we have this classic result. If r of t has a transform s of omega, and then if you bring in this expression into the tau domain, its transform is 2 pi r of minus omega. So for example, if you take this function r to be f of t or r of, let's say f of t in this case, a pulse of width t, then it's a Fourier transform. You can quickly do minus t by f of omega is plus t 1, let's say e raised to minus j omega tau d tau. So that's e raised to minus j omega t by minus j omega, minus t by 2 to plus t by 2. So that's minus 2j sine omega t by 2 over omega. So I can write this as sine omega t by 2 over, there is a 2 here, so I'm going to write it like this, omega by 2. And if I multiply by t on both the sides, I get this. This is the classic definition. So notice that if I make this of height 1 over t, then this will be multiplied by 1 over t. So in time domain, if you have this pulse of height 1 over t, its transform is Sinc omega t by 2. And so consequently, if you put a t equal to 2, which is, so this is 1 over t, this is t equal to 2, so this is minus half to plus half in the t domain. Here you have a sinc t. So, I'm sorry, sinc omega, because t is 2. So if using this result, this identity, sinc t, if you bring this up here, or sinc tau, its transform is given by 2 pi, so that will be pi here, multiplied by minus half in the omega domain. This is the transform of the sinc. So let me call this to be h of omega. Okay. So we can, I'm going to start with problem number 2, in fact, since I have done this much. So again, I'm going to use some well-known results. So the transform of this is the transform of this convolved with the transform of this, because if you multiply two functions in time domain, the transform is, so for number 2, let me call this R1, R2, etc. R1, R2, R3, R4. So S2 omega, if it is whatever, the Fourier transform of this is the Fourier transform of e raised to minus alpha tau convolved with this function, h of omega. So we'll come to that in a minute. And the transform of this is easy because this is integral minus infinity to plus infinity e raised to minus alpha tau cos omega tau plus j sin omega tau. This is an even function, so the odd portion goes away. And so this transform turns out to be 2 times integral from 0 to infinity. Then to do this, write cos omega naught t at this. So this is cos omega t. Cos omega t as the real part of e raised to j omega t. So this becomes 2 times the real part of integral from 0 to infinity e raised to minus alpha plus j omega multiplied by. So you do not need the absolute value anymore because it's only in 0 to infinity tau d tau. So if you do this integration, it is 1 over alpha plus j omega multiplied by this function. Top limit is 0, bottom limit is 1, minus goes away. So this, and the real part of this is alpha over classic result, alpha squared plus omega squared. That's the real part. There is a 2 there. So we found the Fourier transform of this. So the problem is now to convolve this with the rectangular function. So first of all, so we have sine of beta t, so we may want to use this result here. So if you want sine of beta t, I put t equal to 2 beta, right? Because 2 equal to 2 beta, we get omega t. That would come out as here. So we would have beta tau. I put t equal to 2 beta. So this goes from minus beta to plus beta. And the height is, so this is multiplied by, where is it? Here. 2 pi multiplied by the height. Remember, t is 2 beta, so 2 cancels. This is pi over beta. So we need to convolve this with minus beta to beta and pi over beta. So S2 of omega is minus infinity to plus infinity. The transform of this is already here. So we could write it as, if you want one more step, 2 alpha over alpha squared plus omega squared convolved with this function. I'm going to call this h of omega. So that's going to be minus infinity to plus infinity 2 alpha, alpha squared plus omega minus x, right, the whole squared, h of x dx, convolution. But h of x only goes from minus beta to plus beta. And during that portion, this is going to be a constant. So this is pi over beta outside, minus beta to beta. This is now 2 alpha, right? 2 alpha is also outside. So 2 pi alpha in the numerator. This is 1 over alpha squared plus omega minus x squared dx. So this, of course, you can write as omega minus beta, right? When x goes to, if I put omega minus x to be y, when x goes to beta, x goes to minus beta, it is omega plus x. X goes to minus beta, it's omega plus beta. And so the constant is 2. Then, so omega minus x is y. So dx is minus dy. The limits get switched. So we get these limits. Here this is 1 over alpha squared plus y squared dy. This is a standard substitution. You substitute y equal to alpha tan theta. Then dy is alpha sec squared theta, d theta. And alpha squared plus y squared is alpha squared sec squared theta also, right? So this cancels with this. So this integral now becomes 2 pi over alpha beta. And when omega is beta, oh, first of all, once again, this is over a, so we are substituting y equal to alpha. So notice the limits now. So the top limit is going to be, so this integral, which is, this integral is going to be now, yeah, it's here already. So let's substitute the limits now, because inside is easy. It's sec squared theta cancels, and I already cancelled the alpha, so this is just a d theta. But the limit is, y is the top limit, for example, omega plus beta. So omega plus beta over alpha tan inverse. So that's going to be tan inverse of omega plus beta over alpha. And the lower limit is omega minus, so tan inverse of omega minus beta over alpha. So there is a little more simplification to be done. So we get S2 of omega, I'll write it here, is tan inverse omega plus beta over alpha minus tan inverse omega minus beta over alpha, the whole thing divided by or multiplied by 2 pi alpha over, or 2 pi over alpha beta. So how to simplify the numerator? Right? So let me call this to be, this whole term, this whole thing to be A. So I have, from here I have tan inverse of omega plus beta over alpha is A plus tan inverse of omega minus beta over alpha. So I get omega plus beta over alpha is tan of A plus tan inverse omega minus beta over alpha. But tan A, tan B is tan A plus tan B, which is omega minus beta over alpha over 1 minus, right, tan A, tan B. Tan B is omega minus beta over alpha. So if you cross multiply, you get omega plus beta over alpha multiplied by 1 minus tan A or omega minus beta over alpha multiplied by tan A equal to tan A plus omega minus beta over alpha. And we can solve for tan A. So let's expand this. So first of all, let me multiply it by alpha throughout. So I'm going to take out this alpha, multiply on this side, I get here. This alpha goes away, so I get this expression. And I have another alpha here, so I multiply here, and that's going to hit here also. So I get omega plus beta multiplied by alpha minus tan A multiplied by omega plus beta from the top line equal to alpha squared tan alpha tan A plus alpha multiplied by omega minus beta. So if you expand this, you get alpha multiplied by omega plus beta minus omega plus beta omega minus beta, I guess. Notice that this is omega minus beta here. So this should have been omega. So that's omega squared minus beta squared multiplied by tan A equals alpha squared tan A plus alpha multiplied by omega minus B. So let me collect the tan terms together. So I get 2 alpha beta, alpha beta, alpha beta. Alpha omega cancels here. And all the other, so this is equal to, I'm going to write this as, this goes to the other side. So I get omega squared plus alpha squared minus beta squared multiplied by tan A. Or we get tan A is, which is what we have been looking for, 2 alpha beta over omega squared plus alpha squared minus beta squared. So what is the whole point? The whole point is the spectrum can be written as, we want A. A is going to be tan inverse of 2 alpha beta over omega squared plus alpha squared minus beta squared. Notice that we want this quantity to be positive, because if tan A is positive, A is, we want A to be positive. So we want, if you want this to be positive, all you need is alpha greater than beta. That's the only condition. Okay. So we solve for A, and A is here. So I can rewrite this whole spectrum as, so 2 pi over alpha beta A. A is going to be tan inverse 2 alpha beta over omega squared plus alpha squared minus beta squared. So we know that this will be positive if alpha is greater than beta. Or if alpha, because alpha squared minus beta squared, you just need something positive in the denominator. So alpha greater than beta is sufficient. So in particular, if beta is 1, that's also, what is interesting will be when alpha is greater than or equal to beta. So if alpha equal to beta, then this thing goes away, and you get the spectrum. So we can write e raised to minus alpha tau multiplied by Sinc alpha tau is a valid autocorrelation function, because its spectrum is 2 pi over alpha squared tan inverse 2 alpha squared over omega squared, because alpha equal to beta. And so this is positive, so this is a valid autocorrelation function, and here is its spectrum. So let me also quickly do the one more case, and then you can do the other cases similarly. So let's do the, so in the last problem you have to do this and find out the value of phi for which the whole spectrum will turn out to be positive, and that will give you, that will tell you that for those values of phi, that function is a valid autocorrelation function. So this is an interesting problem with the Sinc. Usually you don't see it, but these are classic problems. So you just do it, that's all. So here you substitute e raised to minus alpha tau cos beta tau, then e raised to minus j omega t, which is cos omega tau plus j or minus j sin omega tau. So the argument is, when you substitute it here, cos is an even function, this is an odd function, this is an even function, this is an even function in tau. So only the odd term is not going to contribute. So first of all we have this to start with. And so this is an even function. So this integral is 2 times the integral from 0 to infinity e raised to minus alpha tau. Once again, you don't need the absolute value here. Cos beta tau cos omega tau d tau. So this, of course, you can write it as integral 0 to infinity e raised to minus alpha tau cos a plus b. So that's omega plus beta tau minus or plus cos a minus b, omega minus beta tau d tau. So once again you can use the real part. So this you can write it as a real part of integral 0 to infinity e raised to minus alpha tau e raised to j beta plus whatever omega tau plus e raised to j beta minus omega tau. Remember, cos is an even function, so d tau. So this will turn out to be a real part of, when you, we can do it mentally, when you multiply this with this, or one more step. So this would be integral 0 to infinity e raised to minus alpha plus j beta plus omega t or tau dt plus integral 0 to infinity e raised to minus alpha plus j beta minus omega tau d tau. So integral is e raised to minus at is e raised to at over minus a. Top limit is 0, bottom limit gives you 1. So this is simply the real part of 1 over alpha plus j beta plus omega plus 1 over alpha plus j beta minus omega. So you just need to simplify this. So the real part is alpha over alpha squared plus beta plus omega the whole squared plus here alpha over I'm sorry, you have to multiply the two and then take the real part. So you have to, so this is going to be, you have to multiply with the conjugate, complex conjugate of this, which would come here. So this would be alpha minus j beta, so that's a bit tricky, over alpha squared plus beta plus omega the whole squared plus alpha minus j And this, if you do this, I'll just write down the expression I have. Yeah, which would be, of course, alpha all. So this is going to be as I had before, in fact, alpha squared plus beta plus omega the whole square, because the real part adds up. So you can see it's already, if you want to simplify this further, this turns out to be 2 alpha. You just cross multiply and expand, etc. Alpha squared plus beta squared plus omega squared. So the easiest way this would be, if you expand this here, if you want to cross multiply, this is alpha squared plus beta squared plus omega squared minus plus 2 beta omega multiplied by alpha squared plus beta squared plus omega squared minus 2 beta omega. So that's where I was going. So when you multiply, you'll get alpha squared plus beta squared plus omega squared, the whole squared, minus 4 beta squared omega squared. Now, it is pretty clear this is positive. You can also expand it another way and show that the denominator is positive, numerator is positive. So consequently, this is the spectrum. And the function, this is of course S1. So this is positive, and this is a valid autocorrelation function. This will be a valid autocorrelation function if alpha is greater than or equal to beta. So of course both equal to 1 is fine too.